So, that is what I am trying to say here. So, find A H A inverse, it will give you a subgroup conjugate to H. You start with a group with a subgroup and generate other conjugate groups out of this, and then if you also find that you do not get anything new, the conjugation gives you the same subgroup in the context, in this context it is H2, then you say that that subgroup is a normal subgroup or an invariant subgroup. Okay. So, the left coset of the say subgroup will be same as the right coset if H is a normal subgroup. So, we have already done this, find the conjugate subgroups of the symmetric group. I have explicitly done it for you. Okay. This is something which I want you to check. The set of cosets, okay. So, let us write it out, of a normal subgroup. What is the set of cosets for a normal subgroup? This was multiplied by E, normal subgroup was H2. I just want to look at the set. So, this is one, the other one will be somebody with A, right. So, what you can do is you can write H2 multiplying a set which is E and A. So, this one, this set is also a, so E is a candidate for the first coset, A is a candidate for the second coset. Okay. By that I mean you multiply A with all the elements of H2, you can equivalently call this as some kind of a set SE, and you can call it as an SE. Okay. So, this SE is also a group because identity element does not change the subgroup nature, but this is not a group, right. You get what in the H2 of A? SA set is what? Someone? H2 with A. So, you will have an A, AB, AB squared, right, or the other way around. The way I have written it, it should be, it is the same because it is an invariant subgroup. Okay. So, the corresponding candidate is SA, okay, the A. So, you can see that if you take a group, this one is actually a subgroup. You all agree? EA is a subgroup. Another way in which we write this, so we take a group G, we take a subgroup, in general if you take a disjoint union of cosets, and if H okay, so this implies H is invariant subgroup, okay. This happens, then you can show that G mod H, this is what we call it as a factor group, factor, the factor is going to be candidates of the cosets. Okay. And this will be satisfying the group properties. It will also be a group. Okay. called factor group. You can always factor by any arbitrary subgroup, okay. It is not required that it should be an invariant subgroup. That will not be a group. Only if H is an invariant subgroup, you can show that this factor has group properties. That is what is happening here, okay. So, the factor, so this is SA and this is SC. In this particular example, you have a H2E union H2A in this particular example. So, you find that factor group is E and A, which is nothing but G mod H2. Okay. Yeah. Is that clear? Any questions on this? So, the factor will not be a group unless this subgroup is an invariant subgroup. You can do the other way around. You can do G with H1 and check it out what happens, okay. And this will not be a group. H1 is not an invariant subgroup. Okay. So, with this simple example of the first non-trivial non-commuting nature with 6 elements, I have tried to give you so much of data, right. So, we started with, I initially made a simple abelian group, then I made it non-abelian. Abelian group, if you take an abelian group, what are its subgroups? What are its conjugate elements or conjugate subgroups? These are questions which you should see for the cyclic group. If you take a cyclic group with 2 pi by n, which is non-trivial, so let us take n to be something like a prime number, okay. You can take C5, will it have subgroups? Why did I take a prime? Why did I take a prime? Lagrange's theorem says that if you have a prime number, then you cannot find a subgroup. Am I right? If you have C5, order of C5 is what? 5. Subgroups order should divide the 5. The only possibility is 1 or 5, which is trivial. Identity element is a subgroup, total group is a subgroup, right. So, here you can start seeing what is going to be your, every element will be like a coset, you can't further break it up. But if you do, let us say C6, C6 is what? It is generated by rotation by 2 pi by 6, 2 pi by n is for general. So, now you can start seeing whether there are subgroups, order 6 group, but that order 6 group has nothing to do with the symmetric group. Why? That order 6 group is a cyclic group which is abelian, right. So, just think over these concepts. So, look at this group C5, look at C6, check for, these are all abelian groups. If you have abelian groups, you do not have these conjugate elements. Why? Abelian means that this can exchange with this trivially, okay. Whether it is invariant or not invariant, it can exchange. So, everything will be self conjugate. Even if you find subgroups in abelian groups, you will find them to be self conjugate. You will not get conjugate elements So, do the simple exercise for C6, I will give an assignment on Thursday. So, do it for C6 and compare and contrast with what we did for the symmetric. Okay. Okay, so that brings me to a concept called, so what have we seen? We have seen that we have a symmetric group G, we have a subgroup which is H2 which is a subgroup of G, right. You can try to write the G mod H2 to be a new group K, okay. Let us call it as a new group K, factor group. If you want, we can call it as a factor group F. We have seen that it is a group, right. EA is a group, subgroup. It has all the group properties for this particular example. Suppose I write a map from G to F using a map phi. Okay. Let us take a map which takes you from the group G, order of G is 6, order of F is 2. You are all with me? E and A, order of that is 2. If you try to write this map, then we call this map, what is the meaning of this? Phi of G1 should be an element of F. Correct? And what else is required? Phi of G1 combined with G2 should be same as is that right? It's true for identity element. So, we need it to be, these are all elements of F and this is element of G. You multiply, find a new G and then you should get a element of F, right. Okay. So, now this properties is what we call it as a homomorphism. E is an identity element, okay. So, I am calling this as identity element. Can somebody tell me what this means? What is this phi called? So, if you have a subset in G which gets mapped to an identity, so let us draw it here. Let me draw the group G, let me draw the group F. Group F has only two elements, identity and A, okay. I am just calling it as capital just to distinguish this from here, okay, nothing more. Here you will have E, B, B squared, then what else? Okay. I am trying to say that there are 3 elements here which gets mapped to the identity element. So, this is not 1 to 1 on 2, right. What else happens? Okay. Yeah. Phi of? Did I do? Sorry, phi of H2, sir. Thank you. This has to be phi of H2. I am looking at specifically the symmetric. Okay. That is what I am shown. Okay. So, that was just. So, this is what we call it as a map, where when I compose this element with any of these elements, E times AB will give me AB, E times A will give me A, and this map is correct. Okay. So, this is what we call it as a homomorphism between G and F, and the set of elements which maps to the identity element, that set is called as the, anybody who has done, kernel of the. Okay. So, this E B B squared is mapped to identity, okay. Anything phi of this set is mapped to identity, okay, equal to, okay. We call this as a kernel. Given a homomorphism between two groups, if the kernel is non-trivial, okay, the set of elements of the group G which gets mapped to the identity is called the kernel of this map. Okay. So, this is what is the definition of a homomorphism. Sometimes you would have seen isomorphisms. When will it be isomorphic? If the kernel is just having only one element, which is identity. So, suppose I have a group G1 and G2, you have a set here and a set here. Identity element gets mapped to identity element, and so on. Then we say that phi 1 is isomorphism, okay, and you can sometimes denote it as G1 as isomorphic to G2, or G1 and G2 are actually, one you can see it like a rotation by 90 degrees, another one you can see it like a cube root of unity, sorry, fourth root of unity, and both are one and the same. It may look, meaning may be looking different, but those two are related by a map. Okay. So, 1 to 1 if you get, then you call it to be an isomorphism. If there are many elements which gets mapped, still it is the group G1 is homomorphic to this one, G is homomorphic to F, and the kernel is given by the invariant subgroup. Okay.